Somewhere off the coast of Qingdao, a ship the weight of 18 fully loaded Boeing 747s lifted itself completely out of the ocean, standing on four steel legs like some kind of mechanical spider, and then calmly hoisted a piece of machinery taller than most skyscrapers nearly 200 meters into open air. If you saw this happen with your own eyes, you'd assume it was impossible. Engineers spent years making sure it wasn't. By the end of this video, you're going to understand exactly how a vessel this massive manages to stand dead still in the middle of open ocean, how it lifts loads heavier than the Eiffel Tower to heights that would make a skyscraper elevator nervous, and how it does all of this in waters that produce some of the most violent typhoons on the planet and somehow keeps working right through them. There's a moment coming up involving what happens underneath this ship's legs that genuinely alarmed engineers the first time they encountered it elsewhere in the industry, so stay with me for that. And if stories about engineering pushed to its absolute limits are the kind of thing you enjoy, it costs nothing to hit subscribe before we get into it, so you don't lose this channel later. The ship is called the Gang Hongping 5, delivered in August of 2024, and to understand why it exists at all, you have to understand a problem that had been quietly building inside the offshore wind industry for years. Wind turbines had been getting bigger and bigger, generation after generation, because the math behind bigger turbines is simple and compelling. A larger turbine captures more wind, generates more electricity per unit installed, and requires fewer total foundations to reach the same power output as a wind farm built from smaller machines. For a long time, that trend just kept paying off. Bigger meant better, and the industry kept pushing the ceiling higher. But somewhere around the 18 megawatt mark, that trend hit a wall, and it wasn't a wall made of physics exactly, it was a wall made of ships. The vessels that had spent decades installing offshore wind turbines, cranes mounted on floating hulls, simply weren't built for components at this scale. The towers had grown too tall. The nacelles, which housed the generator and gearbox at the top of the turbine, had grown too heavy. The blades stretched long enough that handling them in anything but calm conditions became genuinely dangerous. And the core issue underneath all of it was motion. A traditional crane ship floats, which means it moves, even subtly, with every wave and every swell. That's rarely a problem when you're lifting a few hundred tons a modest height into the air. It becomes a very different kind of problem when you're trying to lift close to 2,000 tons nearly 200 meters up, because at that height, even a small rocking motion at the base of the ship translates into a much larger, more dangerous swing at the top. Imagine holding a fishing rod steady versus trying to hold a fishing rod steady while standing on a rowboat, and now imagine the fishing rod costs several $1,000,000, and there are people working near where it lands. So the industry needed something categorically different, not a bigger version of the same idea, but a completely different approach to the problem. And that's really the story behind this ship. It's 135 meters long, 50 meters wide, and weighs somewhere around 27,000 tons, numbers that on their own don't mean much until you understand what those numbers are in service of. Because the real innovation here isn't the size of the ship at all. It's what the ship does the moment it arrives at a job site and what it stops being once it gets there. When the Gang Hongping 5 reaches an installation location, it doesn't behave like a ship anymore. Four enormous steel legs, structures that look almost more like bridge pylons than anything you'd expect to see on a vessel, extend straight down toward the seafloor. Once they make contact, hydraulic systems begin pushing against the seabed, and slowly, the entire hull of the ship begins to rise, not the legs sinking further, but the ship itself climbing upward along them, until eventually the whole hull is lifted completely clear of the water's surface. At that point, something remarkable has happened. The ship is no longer floating. It's standing. It has effectively become a fixed, land-like platform sitting in the middle of the ocean, completely disconnected from the waves moving beneath it. Swells can roll right underneath the hull, and the platform doesn't feel a thing. That single transformation, from floating vessel to elevated fixed platform, is the foundation that everything else on this ship is built on top of. Because once you remove wave motion from the equation entirely, you unlock an entirely different category of what's mechanically possible. With the hull stabilized in the air, the ship's crane goes to work, and this is where the numbers start to feel almost fictional. The crane is capable of lifting close to 1,800 tons, and it can raise that weight to a height of nearly 200 meters above the water. Picture the tallest building in a mid-sized city, then picture a crane lifting a load heavier than a fully loaded cargo train to the very top of it, smoothly and precisely enough to bolt components together with the kind of tolerances usually reserved for far smaller, far more controlled environments. These aren't simple steel beams either. The turbines being installed are built by Dongfang Electric, and they represent some of the largest wind turbines currently being deployed anywhere in the world. Once fully assembled, the hub, the central point where the blades connect, sits 185 meters above the ocean's surface. The three blades together sweep out a circle 310 meters in diameter, meaning as those blades rotate, they're tracing a shape wider than most stadiums. And here's the part that actually matters beyond the impressive numbers, the part that explains why any of this effort is worth it in the first place. A single one of these turbines can generate roughly 100 million kilowatt hours of electricity per year. To put that into terms that actually mean something, that's enough electricity to power approximately 55,000 homes from one turbine, while saving an estimated 30,000 tons of coal annually compared to traditional fossil fuel generation. Multiply that across an entire wind farm, and you start to understand why solving the installation problem at this scale wasn't optional for the industry. It was the entire bottleneck standing between where offshore wind was and where it needed to go. But here's where the story gets genuinely more complicated, because building a ship strong enough to lift this much weight is, in some ways, the easy part. Steel and hydraulics can be scaled up. The far harder problem is control, prediction, and precision, because at this scale, small errors don't stay small. They compound, fast, and often in ways that aren't obvious until it's too late. Take something called leg punch-through, a phrase that sounds almost harmless until you understand what it actually describes. When those four massive legs push downward into the seafloor, the entire operation depends on an assumption that the ground beneath each leg is roughly similar in density and firmness. But the ocean floor is not uniform. It can shift dramatically over short distances, with pockets of soft sediment sitting right next to much firmer ground, sometimes separated by only a few meters. If one leg happens to land on a softer patch while the other three land on firmer ground, that leg can suddenly punch downward faster and further than the others, throwing the entire elevated platform off balance in a matter of moments. This isn't some theoretical worst-case scenario dreamed up by cautious engineers. Other heavy-lift vessels operating elsewhere in the world have experienced real emergencies tied to exactly this failure, situations where uneven seabed conditions turned a routine jacking operation into a genuine crisis with a ship's stability suddenly in question. It's the kind of failure that, once you understand it, makes you look at the ocean floor completely differently, as something far less predictable than it appears from the surface. The Gang Hongping 5 was engineered specifically with this risk in mind. Before the legs ever touch down, the seafloor at the installation site is scanned in detail, mapping out variations in density and composition, so the crew has a clear picture of what's beneath them before they ever commit to a landing position. And once the legs are down and the ship begins to rise, real-time pressure monitoring tracks the behavior of each individual leg continuously, so that if one begins sinking faster than the others, the system identifies the discrepancy immediately, long before it becomes a visible problem, let alone a dangerous one. That's just the first challenge this ship had to solve. And honestly, it's not even the one that caught engineers most off guard. Because here's where it gets more complicated. Even once the ship is perfectly stable, elevated, and locked in place above the waves, physics doesn't stop working just because the ocean has been removed from the equation. Consider the turbine tower itself, a structure over 100 meters tall, standing in direct, unfiltered sunlight for hours at a time. Steel expands as it heats, and because the sun only strikes one side of the tower directly, while the opposite side remains in relative shadow, the two sides of the structure don't heat evenly. One side expands more than the other, and the result is a subtle but very real bend in the tower, often invisible to the naked eye, but absolutely significant when you're trying to align massive components at extreme height with millimeter-level precision. Now imagine lifting an enormous nacelle toward the top of a tower that is quietly bending as the sun moves across the sky. That misalignment, small as it might sound, is more than enough to turn a routine installation into a dangerous one. The solution here isn't dramatic, and it isn't a single clever fix. It's continuous. Sensors monitor the tower's temperature and structural behavior throughout the entire operation, feeding that data back in real time so that adjustments can be made as conditions change, rather than relying on a single measurement taken before the lift ever began. It's the kind of engineering that never shows up in a highlight reel, quiet, unglamorous, constant, but without it, none of the more impressive lifting capacity actually means anything. And then there's the challenge of the ship itself tilting, even while sitting elevated on its legs. Moving 1,800 tons of steel through the air, swinging it, raising it, repositioning it, changes the ship's center of gravity from moment to moment. Even with the hull locked into place well above the water, that shifting weight can cause the entire platform to lean, sometimes only slightly. But at a structure this size, holding components positioned with this much precision, even a small tilt at the base becomes a significant problem at the top of the crane's reach, nearly 200 meters away. This is solved through something called active ballast control, essentially the ship's ability to move seawater between internal tanks in a matter of seconds to counteract shifting weight before it becomes destabilizing. What makes this particularly impressive is that the system isn't simply reactive. It doesn't wait until the ship begins tilting to respond. Based on how the crane is moving and where the load currently sits in space, the system predicts the coming tilt before it actually happens and begins redistributing water preemptively. In practice, that means the ship is essentially rebalancing itself in anticipation of forces that haven't occurred yet, sometimes dozens of times over the course of a single lift, a constant, invisible correction happening faster than any human operator could manage manually. None of these systems, the seafloor pressure monitoring, the thermal expansion sensors, the predictive ballast control, operate as isolated components watched over by separate teams. They're unified through what's described as an integrated intelligent control platform, a system that manages ballast, positioning, and crane operations together as one coordinated process rather than as disconnected mechanical functions. And this kind of integration doesn't just improve safety margins, it also improves efficiency in a very tangible way. By coordinating these systems intelligently instead of running them independently, the vessel reportedly reduces its overall fuel consumption by around 20%, a meaningful figure both economically and environmentally, which is fitting in a slightly ironic way, given that the entire purpose of this ship is installing infrastructure meant to reduce reliance on fossil fuels in the first place. Positioning accuracy matters just as much as stability once the ship is elevated, because even a few centimeters of error at the base of the vessel can translate into meaningful misalignment nearly 200 meters higher, at the point where components are actually being connected. To manage this, the ship relies on three separate, redundant positioning systems operating simultaneously, including China's Beidou satellite navigation network, so that if any one system experiences interference, signal loss, or failure, the others continue providing accurate positioning data without interruption. And in the unlikely event that every automated system fails simultaneously, there's still a manual override key that hands direct control back to the captain, a strikingly low-tech failsafe sitting quietly underneath all of this advanced automation, which says a lot about how seriously the engineers behind this vessel took worst-case scenarios. Now here's the part that really puts everything we've talked about to the test, because up to this point, we've mostly been describing how the ship handles reasonably normal operating conditions. The South China Sea doesn't stay reasonable for very long. It's home to some of the most powerful and unpredictable storms anywhere on Earth, and this isn't an abstract risk. In 2024, Typhoon Yagi tore through the region and caused real, documented damage to older wind turbines, a clear and recent reminder that offshore infrastructure here isn't just dealing with routine weather patterns, it's dealing with genuinely extreme conditions on a recurring basis. Any vessel or turbine operating in these waters has to be engineered around that reality from the very beginning, not bolted on afterward as an afterthought. So when a storm approaches, the turbines this ship installs don't simply sit there and absorb whatever the weather throws at them. The blades automatically rotate to face edge first into the wind, dramatically reducing the surface area exposed to the storm's force, essentially transforming from broad surfaces, catching wind into thin blades slicing through it instead. At the same time, the ship itself raises further up along its legs, lifting the hull even higher above the water so that storm waves can pass underneath the platform, rather than slamming directly into it. Between the turbine defending itself and the ship elevating out of harm's way entirely, the whole system is designed to survive conditions that would be catastrophic for less prepared infrastructure. And maybe the most genuinely impressive part isn't simply that the ship and turbines survive the storm, it's how quickly everything returns to normal afterward. Rather than requiring days of inspection, damage assessment, and cautious restart procedures, operations are reportedly able to resume almost immediately once the storm has passed, meaning the enormous investment of time required for installation isn't lost to weather delays the way it traditionally has been throughout this industry. When you step back and take in everything this vessel actually does, scanning the seafloor before ever committing to a landing position, predicting its own tilt before it happens, continuously correcting for thermal expansion invisible to the naked eye, and automatically defending itself and the turbines it installs against some of the most violent storms on the planet. It becomes clear that the Gang Hongping 5 isn't simply a larger version of the heavy-lift ships that came before it. It represents a fundamental shift in how offshore infrastructure gets approached in the first place, treating stability, prediction, and redundancy as core design principles from day one, rather than safety features added on top of an existing idea. And that shift matters enormously, because the 18-megawatt barrier that once stopped this entire industry in its tracks isn't a barrier anymore. Ships like this one are proving that scale doesn't have to mean fragility, and that the next generation of offshore wind, taller towers, wider blades, heavier components, isn't a future possibility. It's already happening, right now, off the coast of China. That's the payoff behind everything we opened with. A 27,000-ton ship capable of standing perfectly still in open ocean, lifting loads heavier than most bridges nearly 200 meters into the sky, and shrugging off typhoons that would cripple older infrastructure entirely, all through a combination of raw mechanical force and remarkably careful, quiet engineering happening constantly behind the scenes. If large-scale engineering stories like this one are genuinely interesting to you, this channel covers them regularly, so make sure you're subscribed and have notifications turned on so you don't miss what comes next. And if you're curious what happens when this same level of ambition gets applied underwater instead of above it, there's another story on deep-sea engineering I think you'll want to watch next. Let me know in the comments what part of this surprised you most, and I'll see you in the next one.